I'm going to talk to you about Gaussian processes. You can see a lot of recordings of me talk about Gaussian processes online as well, so probably some of it, if you watch any of those, you'll recognize some of the material. If not, then hopefully it's okay live as well. So if you are interested as well, if you want to know more about this, Gaussian processes go far beyond machine learning. So we also do this Gaussian process summer school. The next one is in about a month's time. And actually we're covering something called uncertainty quantification too. So uncertainty quantification is a field that's coming out of applied maths and engineering, where they use very often Gaussian process models, but other models as well, as surrogate models for some sort of system. It could be a numerical system, or it could be a real system, but you use the Gaussian process to try and estimate the amount of uncertainty in what you know about the system. And that's very appropriate because that's what Gaussian processes are very good at, and I'll hopefully persuade you of that today. So if you are interested in more, I think that the registration is still open, although it might be full. But you can register for that, gpss.cc, and then you get to hear me saying this stuff again. Okay. So still probably about 10 years old now. The main book from a machine learning perspective for Gaussian processes is the Rasmussen and Williams text. So it's also available online, so if you want to just have a look at it, you can get the PDF and have a read through. It's covers things, I think certainly from the perspective we would have had about 10, 15 years ago, it introduces Gaussian processes. And of course the ironic thing is in the field of machine learning now, we're just regaining the perspective we had 15 years ago, so it's probably very appropriate. Machine learning is more about modeling, and I suspect that this is a model most of you have seen. I think even, depending on what country you've studied in, you may have even seen this as early as 11 or 13 years old, or at high school. And of course this is the equation people typically use for a straight line, where y, some axis observation on the y-axis, is equal to some input x, plus times some scale plus some offset. And that's really fundamental because this is a functional relationship. And I think for me, and this probably isn't 100% true, but for me, almost all the machine learning I do is interested in finding out about functional relationships. And that's why Gaussian processes are important. So this gives us an equation of a straight line, and this has been known for a long time. But I think what's kind of interesting is to reflect on what happened when people first got data. So you can get this data fitted with two data points, because there's two unknowns, m and c, the gradient and the offset, and two observations, a paired value for the x and y, is sufficient to tell you what those unknowns are. So you can sort of get one equation associated with this x, and a second associated with this observation, and a second equation associated with this observation, and you are fine. You can estimate m and c. The interesting thing for not just machine learning, but for data in general, and I kind of think, what is machine learning, right? Machine learning is a group of people that got together and were interested in a particular set of things. What it has become today, I mean, it's not really important what it is historically, I can talk about what I think that is, but what it has become today is the principal technology underlying two fields. One of those fields is artificial intelligence. Artificial intelligence is about replacing humans with evil killer robots. The other field is data science. Data science is about assisting humans with challenges they face to try and understand the world around them by better analysis of data. Now, machine learning is really driving both these fields in terms of where we see the advances in AI that people talk about in terms of digit recognition, face recognition, that I'm sure a lot of you are familiar with. People think of that as artificial intelligence, but there are advances in machine learning, or there are advances in compute power and availability of data. What interests me perhaps more, I'm interested in that as a social phenomenon, but is understanding of data to try and make better decisions. So that's an old field. And it goes all the way back to people looking at the motion of planets around the Earth and trying to say, well, is that new object a planet? Is it a comet? What is it? Trying to identify where the stars are, trying to navigate. And when they were doing those things, so sort of following on from the sort of Kepler's laws of planetary motion, they had fixed laws for how the planets move. And then they looked down telescopes and they might make 34 observations. There's a guy called Piazzi who discovered Ceres, which is a dwarf planet, and he made 34 observations of where that planet was. That's way more observations than you need to actually fit the Kepler's laws of planetary motion. So he had more data than he needs, just like this. And it's interesting to consider what they did, because now we just take it naturally. Oh, well, yeah, people, so what would we do there? Someone shout out what would we do there to deal with the extra point. How would we fit this? How would you talk we fit this at school?
Least squares?
Least squares, yeah. So least squares actually dates back to that same era. So about 216 years ago. And that's one of the things they did. But before least squares, and actually contemporaries, Gauss, who was one of the inventors of least squares, the way he did it was slightly different. So there's actually a few different things. One of the things people suggested is making all the possible fits you can, like this, and then selecting amongst them. So you select the median fit. They had some ideas like that, you know, which is an interesting idea. It wasn't obvious necessarily that they should do least squares. So, okay, so what do I view as what's going on here? Well, we've got 3 points, and then we're trying to satisfy these 3 equations. So this is an overdetermined system. You study these, right? But the person who came up philosophically with the most interesting approach, I think, to how you deal with this, and the one that certainly I follow, it's not the only way of doing machine learning, like least squares. That statement itself implies optimization. You say least squares. We're going to minimize the squared error, right? So that's one way of looking at machine learning, optimization. You formulate an optimization problem that you think reflects what you want to do, what your costs are, what your risks are. So I'm not really going to talk about that side, that's an important side. I'm going to talk about the side that I think that this man is most responsible, certainly for vocalizing the way I go about it. So people should know who this is. People know who that is? Pierre-Simon Laplace. So Laplace, it's good because he invented sort of everything in maths, or at least claimed to invent everything in maths. Yeah, so he's actually sort of quite interesting on this, so you can't probably quite read what he says here. This is an essay from Laplace from about 200 years ago, and it says, in French, nous devons donc envisager l'état présent de l'univers comme l'état effect de son état ultérieur, which is easier for me in English. We ought then to regard the present state of the universe as the effect of its anterior state, and as the cause of the one which is to follow. Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective situations of the beings who compose it, I'm down to here, it's difficult to read for you guys probably, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present to its eyes. People heard that statement before associated with Laplace? It's known as Laplace's demon. And it's the sort of most succinct representation of a mechanistic understanding of the universe. And Laplace is very often associated with it. And it's really interesting what he's saying. The present state of the universe is his use of words, which I think is similar in French. L'état présent, so the present state, that's what we would use state variables we might think about. As the effect of the anterior state and the cause of the one which is to follow. That's the Markov property, which was sort of written down by Markov more formally 100 years later. And intelligence, which he's sort of also, I think, saying on intelligence qui, so intelligence, he's referring to it as an intelligence, so that gives you a feel of AI, which can comprehend all the forces by which nature is animated. So he's actually now talking about mechanistic modeling. And respective situations of the beings who compose it, that's data, so where everything is laid out. And intelligence sufficiently vast to submit these data to analysis, that's GPU computing. It would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. It's an extraordinary statement, and it's an extraordinary claim, and it comes on page 4 on a document, a booklet called A Philosophical Essay on Probabilities. Now pause for a second and consider the fact that this description of the mechanistic way of the universe is page 4 on a philosophical essay on probabilities. A little bit odd, don't you think? Well, that's because it's a straw man. Laplace is saying, don't be ridiculous. You could never do this. And it's so offensive, people, the extent that people quote that as his understanding, or their understanding, his community's understanding of the universe. Because he is actually writing down, you could do all this. if you knew everything. And then it was just, ha, but the universe isn't yet. But then on page 6, 2 pages later, for those that bother to read on, the curve described by a simple molecule of air or vapor is regulated like here in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. He's less pithy here, he's less tweetable in this next section, which is perhaps why this bit is less well quoted. We know that through a greater number of events, a single one would occur. Basically, the whole rest of the document is the fact, key on this point, that the difference between predicting the planetary motion and trying to predict the motion of molecules of air is our knowledge of what's going on. Actually, in Laplace's time, they did not have a good understanding of gases. Kinetic theory of gases is about 50 or 60 years before. And of course, Boltzmann was pilloried for believing in particulate theories of gases, right? So he's talking about molecules at a time when people don't even believe in molecules. So later on, of course, it turns out that our big thermodynamics, our kinetic theories of gases, are based entirely on probability. That's not necessarily how physicists represent it, but statistical mechanics is in that domain. So that's a domain where we have almost total ignorance, but it doesn't matter because we can represent our total ignorance with probability distributions, sufficient statistics, temperature, pressure, these sort of aspects, right? Now, the interesting thing about the real challenges of machine learning are the worlds between the planets and molecules. So things like computational biology, where you're looking at cellular systems, or things like trying to understand a complex system where it's not totally deterministic and it's not totally random. And this is, I think, what interests me about these domains. Now, this is Laplace's solution. So he was interested in probability, motivated by gambling. And then he was interested in astronomy. I mean, when you're a mathematician in those days, you've got to be interested in everything. And by the way, today, for people doing machine learning, you're in the same position. Like, we have not yet people doing data analysis in modern ways. Of course, the statistics. But statistics is about is more focused on when you rigorously collect data to answer a particular question. The challenges of data science, which have moved on, are where you're just given the data and it wasn't really explicitly collected and you're trying to do something. And we have now an access all areas license, just like Laplace had it. We get to go in wherever we like and try and deal with data in there. It's a really wonderful time to be in this field. So what Laplace did is he turned this situation into an overdetermined system, and this is very explicitly what he did. He added variables to represent the difference between his model and the real world. So I've called them epsilon, and we might, later on in the game terms like noise or whatever. But what Laplace is saying is there's some ignorance. You've got your knowledge, which is encapsulated y equals mx plus c, and then there's ignorance about the difference between that and the real world, which is all associated with the atmosphere moving around when you're making observations of planets. And I'm going to represent that by probability, and I'm going to call that epsilon. And that is the sort of foundation of stochastic modeling. So in statistics, you then might make an assumption that epsilon was identically and independently distributed. Laplace made that same assumption, and Gauss made the assumption that it was Gaussian distributed, although he didn't call it that because Laplace actually developed the Gaussian distribution before Gauss. So it's ironic that it's all called after Gauss. There you go. He was very clever too. Now what I like about this framework, and that we some sort of forget these this is how people thought about this when they were faced with them with those fundamental problems, how they were going to deal with them, how they thought about it philosophically. But there's a lovely duality between that and something that then leaks over into the model. So another situation we might get is this may be our model, but we might only have one observation. So we just have y1 is equal to mx1 plus c. So now in this situation, we can compute m if we were given c. So if I give you any particular value for m, you can tell you what the c is, right? So I'm just showing you some, different values for c. I can show you what m is. So I'm just showing you for different values for c. Now, once again, we can pull the same trick. So because of that, what I can do is I can put a probability distribution over the missing value c. So what Laplace was proposing here was introducing a new variable which represents the difference between what we observe. We call it the residual nowadays, right? That's what a statistician would call it. So maybe we wouldn't call it that, we'd call it a noise, whatever. But he's introducing a probability distribution for that unknown. He introduces the unknown and then introduces a probability distribution for it. The way I pursue machine learning is the same thing. I have an unknown variable, the offset, and I introduce a probability distribution for it, and given that, now that's giving me a distribution over possible values of n. And that's known as the Bayesian approach to machine learning. It's a really stupid name because it makes it sound like a cult or a religion. And putting an Ian on the end of anything makes it sound like a cult or a religion. Christian, Bayesian. It's not a cult or a religion. It's a natural way of dealing with uncertainty. It has its challenges. What are the challenges? Where did this thing come from? Where did this distribution over C come from? But those challenges are no different from non-Bayesian approaches. Where does your objective function come from? Where does the thing you're optimizing come from? If you just use maximum likelihood in these models, where does your likelihood come from? Those are the challenges of modeling. That's what you're here for, to become experts in how you deploy those models alongside data. That's no different from Bayesian modeling as it is for any other kind of modeling. And when people say it is, it makes me very angry. So don't say it. The reason why people think it's different is because Bayesian techniques have been quite widely applied to traditional statistical models, like things like logistic regression, which existed as a likelihood that people had accepted. Like it was a thing that when they first learned, someone told them about logistic regression. And if you do Bayesian logistic regression, you then have to add a new thing, put a prior on it. And so people go, oh, where does the prior come from? Yeah, but where did the likelihood come from in logistic regression? It's the same challenge, right? And you must never forget that. It's always, if you forget that, then you're not doing your job as modelers properly. Statistics is slightly different from... Actually, a statistician is trying to avoid introducing a model historically. Nowadays they will be very often, but the earlier statisticians were trying to avoid introducing a model. They were trying to ask questions about data. So they use techniques like randomization and then hypothesis testing, which tries to be as model-free as possible. It often isn't. Which is why there's a bit of an aversion in some domains of statistics, but many of the leading Bayesians are statisticians as well. So you have to be careful about generalizing, but generalizing is our business. Okay, so what is a Gaussian process? So a Gaussian process is an approach where instead of saying I'm just going to deal with this difference between my model, the y equals mx plus c, and the world with probability, what you say is, or instead of saying, oh, I can't deal with c, so let me just deal with c as probability. A Gaussian process is an approach that says, I'm going to say that the relationship between my observations y, and the easiest way of approaching it initially is through regression problems, but you can do classification problems and dimensionality reduction and various others. But I'm going to say my observed data y as a function of x is given by some unknown function plus some corruption. Now, what we're going to say is, instead of just putting, like Laplace initially did, a distribution, probability distribution over this unknown corruption, we also place a probability distribution over this unknown function, over the whole thing. Now we end up with some parameters of that distribution, so we do end up with some parameters. But philosophically it's a little bit distinct from what people traditionally do. It's actually, Laplace did it naturally. Laplace, when he did later analyses, he would do this without even pausing to think, right? The reason you might not want to do it is if you actually have a particular interest in the function and its actual parameters. So in statistics, very often, if you have this sort of relationship, you might be trying to predict the rate of disease as a function of things like whether people are smoking or drinking alcohol, or what their socioeconomic status was, and you might be interested in the parameters of this model specifically. And in those domains, very often people don't like putting distributions over. Okay, so let's contrast that with the classical sort of objective function. This is if I remember this correctly, this is the hinge loss for the support vector machine, where you optimize this thing directly. So what you're saying in this case is you write down this objective function and you say, I want to find parameters such, so this is like the hinge loss of a classification problem where y is the classifier for a support vector machine, where this is the parameters of support, a linear support vector machine, and this is the weights of the inputs, and this is the sort of bias on the outputs. And you optimize that thing directly. And that's written down as a sort of relaxation of the counting the number of mistakes. So it's philosophically a different approach. But the nice thing about machine learning is, despite different philosophies, people historically have mingled together and discussed these different approaches to learning. Whether that'll change, I don't know. So, I'm really keen personally when I think about machine learning on conceptual separation between model and algorithm. Or model and prediction, or model and data, I don't know. So the model is how you encode the regularities of the universe. So that's what you bring to the equation, as it were. You're given some data, and you have to design a model which needs to be combined with that data to make a prediction. The algorithm is very often, from a technical sense, this isn't actually how public understands the term algorithm, but the algorithm is very often how you combine that model with data. So, for example, something that interests me is, put your hands up if you think principal component analysis is an algorithm. Okay, put your hands up if you think it's a model. 2, 3, no, if you've never heard of principal component analysis, that's the rest of you. So, principal component analysis, most people, okay, let's try that again. Put your hands up if you think principal component analysis is an algorithm. Yeah? Okay, put your hands up if you think it's a model. Yeah, interesting. So I think that's the sense I get. Most people think of it as an algorithm. Principal component analysis is compute the sample covariance of your data, compute the eigenvalue decomposition of that covariance, and project your data to visualize or do whatever on the eigenvalues. That's an algorithm, for sure. That's not principal component analysis. That's an algorithm. If you read the paper on principal component analysis, there's a large amount of work talking about a latent variable model, for which that happens to be the solution. And we'll talk about that in the third lecture. Now, it's interesting because understanding the model there has always been lost. But our models, there are about 5 different models underlying PCA. PCA is a really odd situation. If you think of it, as people seem to, as an algorithm, the eigenvalues of the sample covariance matrix, eigenvalue decomposition, that's definitely an algorithm to me. But there's about 4 or 5 different models of the universe that lead to that same algorithm. And they all end up being called PCA. But the original paper described the model. But I guess it's become thought of as an algorithm because there's lots of different interpretations. But bearing in mind that interpretation, so that's okay. I don't care what you think PCA is, personally. I just ask. But it's okay as long as you don't forget that when you're applying the algorithm, somewhere behind it there's a model with assumptions. And Bayesian modeling makes that really explicit. There's disadvantages to making that explicit, big disadvantages in terms of compute, but it's useful to sort of bear it in mind. And if your model isn't explicit, then you should be very careful. So here's my extremely short overview of Gaussian processes. So the approach of, and it's also sort of overview of Bayesian influence. So the approach we take in a regression problem is we have a way of generating functions. That's a probability distribution over functions. We'll go into a bit more detail on that in a moment. But for the moment, we just have a way of generating functions. And what we're interested in doing, so I've generated 1,000 functions. So this is my model of what functions look like, right? These ones happen to be stationary, very smooth. Not all functions look like this. There's no linear functions in there. But I have to have a model. I have to have a belief in what's going on. So there's 1,000 examples from that. Now someone gives me data. Okay, so here's 3 data points. And what I do is I throw away all functions that don't fit with that data. It's very simple and sensible, isn't it? I happen to do that mathematically. That's the process of Bayesian inference, actually. So what we have here, this is sometimes known as the prior, I'm so keen on the term. Prior, this is the data, and the relationship between how close is close enough is specified by the likelihood. Yeah? That's typically how we do it. And then what we're seeing here is samples from the posterior distribution. But the way I'm doing it in this case is actually an algorithm known as sort of, ABC, approximate Bayesian computation, is I'm throwing away all functions that don't come close to those 3 data points. Now you can see why I used only 3 data points, because I've only got 1, 2, 3, 4, 5, 6 functions left out of 1,000. So my rejection rate is very high. So this isn't normally a very efficient algorithm. To make this algorithm efficient, you have to do a lot of work, and that's the field known as ABC, or approximate Bayesian computation. Now, the beautiful thing about a Gaussian process, So this is always what you're doing in Bayesian inference. And you can do this for any model, right? You can write a simulation in code, which is now your model, and you can see how close it is to data, and you can throw away simulations that don't fit. That's why ABC is an interesting area. You don't have to have a mathematical representation of your model. The beautiful thing about the Gaussian process is you can do this mathematically through linear algebra, which is really incredible. Now, it's about the only model that I think it's so trivial to do this, because Gaussians have lots of special properties that we'll look at. And the fact that you can get nonlinear functions out in this way is quite a powerful thing. This is why we like it, this is why they're good ways of handling uncertainty. Computers are, in a sense, in a large sense, you could just describe a computer as a machine for doing linear algebra. Whenever you look at talks from even all this stuff you'll see now with NVIDIA, so doing special deep learning modules for computing the inputs to neurons, they're just matrix vector multiplications, right? So everything that's in a GPU, broadly speaking, is just fast linear algebra. So you've got access to a large amount of compute that is tailored at doing linear algebra. So actually, Philip Pennick was the first person who I saw put it so explicitly like this. Even if you don't believe in this model, you've got a compute machine that is designed for solving this model. So it would seem a shame not to try using it in a similar way. So that's my full introduction to Gaussian processes. And that was the sort of philosophical approach that I take, which you don't have to agree with a lot. If everyone did the same thing as me, it wouldn't be a very interesting world. So you can do something different. That's one of my philosophies. But it's just to understand the different approaches that people are taking with machine learning. So any questions at that point before I sort of go into more specifics on Gaussian processes?
The way you describe ABC is it fundamentally different from rejection sampling?
No, it's the same. It's the same core idea. But in ABC, you typically can't compute the likelihood. So what they do is they define ways of computing the difference between the actual simulation and the samples, and those ways are often based on sufficient statistics of the samples. So there's an layer of complexity to try and. Most of ABC is focused on trying to reduce the rejection rate from rejection sampling. But rejection sampling, in some sense, is the purest Bayesian algorithm. Yeah. But it's very efficient. So the domain of ABC is about making it more efficient. Other questions? Anyone work on ABC? Cool. Where are you based? France. Good. So you like the class? Was my French accent good? I had a French girlfriend once. And when I tried to speak French, I sounded like a pervert. So I tried to reduce my accent a bit, and she said, "No, you sound like a German." And I wasn't sure to the French, which was worse, so I shouldn't speak French. I look at all these terrible things. Now we're Brexiting in the UK. Apparently, I can do this. Okay. Actually, Laplace is my favourite scientist, and Gauss may be my second favourite. So. Multivariate Gaussian. So we're going to start thinking about multivariate Gaussian. So we're going to consider a Gaussian with a particular structure of covariance matrix. And that's really important. To me, why don't people use Gaussian processes much? Because Gaussian is such a boring distribution. Everyone thinks it's a really boring distribution. You're introduced to it at a really young age, and it seems really tedious. It's the most uninteresting piece of mathematics. It's really, really badly taught. And I hope to persuade you that it's much more interesting than you realise. And the reason is because before, you focused on the mean. But all the interesting bits of the Gaussian distribution are in the covariance and how you manipulate covariance. So we're going to be considering a Gaussian distribution, starting with a Gaussian distribution with a particular structure of covariance matrix. And we're going to generate a single sample from that 25-dimensional Gaussian distribution. And then we're going to plot those points against their index. So this is what it looks like. Now on the right here, this is a heat map visualization of the covariance matrix. Some things to note is the diagonal I've set to 1, so it's actually a correlation matrix. That's the definition, a normalized covariance matrix. So it's a correlation matrix, although in general it doesn't have to be. I've just said it like that for convenience here. What you'll see is that points who are close in index are strongly correlated, and points that are far in index have sort of zero correlation. So this 25th point is not under the distribution correlated with the first. Of course, just by sampling coincidence, it happens to be slightly correlated with the first, right? But what neighboring points are, they're always correlated with each other. And the effect is, by structuring the distribution, the covariance matrix in this way, by saying if you are neighboring in index, if you are close by in index, you are strongly correlated. And if you are far in index, you are more weakly correlated. Then you start to see something that looks like a function. And it's a sort of reasonably surprising thing, because I think most of us are used to Gaussian densities as being used for noise. And to sample something from a Gaussian distribution that looks so smooth and so much like a function. Of course, it's not a function because it's 25 discrete points. But you are hallucinating, I suspect, little points in between and joining up those points. It looks like a function. So that's the first aspect. And so why does that come about? Now, this is the first sort of really important property of a Gaussian distribution over some data. So this is f. I'm using f to mean our noiseless function, right? Y would be the corrupted function, which would be our data. F is our noiseless function. So I want to look at 2 points of f. I'm just going to look at these 2 points here. Now this is a joint distribution over f1 to f25. But I'm now interested in only f1 and f2, for whatever reason. Integrating over high-dimensional spaces, integrating out 23 dimensions from a high-dimensional space is typically very, very difficult. That's the major challenge in Bayesian inference, integrating over high-dimensional spaces. It was the major challenge in designing atomic bombs, which is why they invented the metropolis algorithm. It's always been a big challenge. The amazing thing about the Gaussian density is that the marginal distribution of f1 and f2 is given by, I don't know if you see that coming in, but just by looking at those, that section of the covariance associated with those two. So what I've got here is, this is the covariance between f1 and f2 is up here in this block for these 2 points here. It's the joint covariance over everything as a color map. The covariance of those 2 points is just given by that, which is amazing. That's why the covariance is so fundamental. So the covariance matrix is not the only way of representing a Gaussian. There are lots of other ways of representing Gaussians and indeed Gaussian processes, which we'll touch upon briefly. But this property of the covariance matrix is extraordinary. This does not work for the inverse covariance. The color there, sorry, is a little bit, these are slightly lighter than that. So we'll see that now when I turn them into numbers. This property that the covariance marginalizes in that way is very special, and it's what allows Gaussians to be a process. Because once I'm down to these 2 points here, I could have integrated out 23 million points instead of 23, right? So I don't know at this stage whether I'm looking at 2 points sampled from, I've just been given 2 points sampled from a 25-dimensional distribution or a 25 million dimensional Gaussian distribution. And that's a very special property of Gaussian. The covariance amongst those two, those elements would not change regardless of that case. Very, very unusual. It's one of the things that lets them be processes very easily. So here what it's saying is that these points, I haven't told you where the covariance is coming from, but this is showing us that the correlation between f1 and f2 is very, very strong. We can visualize how strong by taking a sort of, plotting f1 against f2 and giving you a single contour of this probability distribution, which is showing you the correlation. So this correlation is showing just how strongly correlated f1 is. F1, which is on this axis, is 1, then the distribution over f2 means it's going to be around about 1. In fact, f1 in our plot there was minus 0.313, and I've drawn a line on this plot to represent this distribution. Now, physically, graphically, you can think computing the distribution over f2 given f1, computing the conditional distribution, as slicing through that Gaussian distribution, right? As taking a slice through this Gaussian hill. And what I'm going to show you, and renormalizing, is the renormalized slice of that. That's the conditional distribution of f2 given f1. Yeah? Make sense? Now the interesting thing about that is we've just done some machine learning. If that Gaussian was our covariance matrix, our model, so it's a zero mean Gaussian. Sorry, I should have emphasized that. This Gaussian is zero mean. There's no mean on this Gaussian distribution. It's zero across all these things. Zero mean Gaussian distribution with this covariance matrix. And I have one data observation of f1 is minus 0.313. I'm getting a prediction of what F2 is. And the prediction is this Gaussian density. Yeah? Does that make sense? So the training data here is F1 and my test point is F2. Now interestingly, this is like that linear situation I showed you at the beginning when C was missing. I'm managing to learn with one data point because I put a probability distribution over the model. So I can still make predictions even though I've only got one data point. Of course those predictions are conditioned on my model. So if my model is wrong, these predictions will be bad. Okay, and that was where F2 actually was. So assuming I was just given F2, we actually had F2 as well, but assuming I was just given F1, but F2 ended up here. So it ends up nicely within this distribution here, right? Now, that was the sort of graphical definition of what's going on. This is the mathematical. So the mathematical says, this is another really special property of Gaussians. The conditional distribution of a multivariate distribution is not normally necessarily within the same class of distributions as the multivariate distribution. So it's not necessarily the case that if I have a joint distribution where F1 and F2 and I ask for the conditional distribution, that conditional distribution will be in the same class. For Gaussians it is. All the conditionals of a Gaussian are Gaussian. And that's another unusual property. I want to say unique, but there may be other distributions or special cases. So it doesn't matter where I condition. I could condition along any of these axes. My distribution is always Gaussian. So the mathematical form of that conditional is as follows. So my prediction over where I think F2 given F1 is, this is the zero mean Gaussian, again, joint distribution over F1 and F2, is given by something relating to the data F1. This is the mean of the Gaussian, the posterior mean. So although the prior mean was 0, the posterior mean is not 0, as long as there's correlation between the two. So K12 here is this element here. This is K12, this is K21. K11, K22. I'm just plugging those elements from the covariance in to give me the prediction. So F1 is K12, which was 0.96, over K11, which was 1, times minus 0.3. So the mean is, well, if the correlation was 100%, the mean would be identical, right? That makes sense for 100% correlation. The variance, though, of the distribution is important as well. So the variance is equal to the prior variance of F2, which is K22. So this one here is the prior marginal variance. If I marginalize down to F2, if I cut out these two, if I just want the marginal distribution of F2, it's just variance 1, right? So the marginal distribution of F2, without observing anything, is just zero mean variance 1. But the conditional distribution starts with that marginal variance, which is 1, subtracts 0.96, the correlation, squared, and divides by 1. So 0.96 squared, I don't know, is about 0.9 or something. So this is 1 minus 0.9, something like that, 0.1, roughly. That's the variance, so the standard deviation would be a bit larger. So this is where the joint density variance is given there, as was implied by my description. Now, a couple of things you can see about that. If the correlation between these two is 100%, if K12 is 1, F2 is equal to 1 over 1 times F1, so it's equal to F1, and the variance is equal to K22 minus 1 over 1. K22 is 1, so that's 0. So if the correlation was 100%, you would just predict that it's the same. Makes sense. If the correlation was 0, then F2 given 0 over 1 times F1, the mean is 0. K22 minus 0 over 1, the variance is K22, the prior variance. So if you've got 0 correlation, you basically say that I get no information from F1 to given to F2. So that makes sense. So here's the same sort of process for a point that is less strongly correlated. So this is F5, which is correlated only 0.5. Now 0.5 is actually quite a strong correlation for a statistical analysis. If you were to do a bunch of data analysis in the lab and get a correlation 0.5, you might be quite excited by that if you could show it statistically significant. But you'll see that in terms of this correlation here, in terms of the conditional distribution, it's much, much less informative. So actually, this distribution over where F5 is, given F1, is much more diffuse. We'll sort of see why that is in the equation in a moment. But look at where the actual data point was. It wasn't even, F1 was negative, F5 wasn't even in the same quadrant. Right? So actually, the behavior of these things as the correlations drops is quite weak. When the correlations are strong, it's very, very strong. So the reason why that variance is going high is because, look, the correlation is squared. So that 0.5 times 0.5, 0.25, the variance is going up quite rapidly as the correlation goes down. Back towards the prior variance. Okay, now in practice, this isn't what we do. We don't normally predict on one point given another point. We predict on a whole range of test data given a whole range of training data. So I can do that sort of conditioning in a multivariate Gaussian too. It just, instead of simple scalar operations, I get matrix operations. And these are the burden, Gaussian process burden, solving these, right? Because what you'll see here is we've got a prediction over some test data, given some training data, where our joint covariance now, we haven't said where the covariance is coming from yet. So just take the covariance as given. The covariance for our training data is this. The cross covariance between our training and test data is this matrix here. So this is a square matrix. This is potentially rectangular if we don't have a different number of test points from our training point. This is square, which is the prior covariance of our test data, and this is rectangular. So now our predictions over our test data given our training are of the form of a multivariate Gaussian, and the multivariate Gaussian says that the mean is given by the training data times the inverse of the prior covariance. Inverting that is an order n cubed operation where you have n training data multiplied by the cross covariance between the two. Now notice if f star was equal to f, this would be just kff, and this would be the identity, and you would recover f as your mean. Yeah. The covariance, and notice it is a covariance. These are not independent predictions; they're jointly correlated predictions. Is equal to the prior covariance over f2 minus the cross covariance between f2 and f1 times that inverse times the cross covariance again. So this matrix here is n by n, but this matrix is sort of n star by n, and this matrix is n by n star, so this resulting matrix is therefore n star by n star. This is guaranteed positive definite. Okay, otherwise it couldn't be a Gaussian density. So this is how we make predictions in Gaussian processes with no noise. That's the mathematical setup. It's 2 lines of MATLAB if you've got your covariance function already. So actually, it's trivial, but there are 2 problems. One is you need to be able to store all your training data. So this matrix KFF is n squared in storage. And storage often gets you tend to run out of space before you run out of time. Is that Louis Armstrong? We have all the time in the world? No. Well, we have a lot of time. So we can run, so even though the inverse is cubic, what we can have, we run out of patience before before too long, but basically it turns out to me when I try these things is I run out of space before I run out of patience on the computation of the inverse. So basically n squared on space is actually a big problem. So if you've got 1 million data, that's what it is. So in Britain that used to be called a billion, but now in America they call that a trillion or something. So it's a million, whatever, which is quite a lot. So we want to be able to go in data science to billions of data, and that's a big challenge for Gaussian processes. One of the big areas we do research on in my research group, making approximations at last. So that would be the sort of form that we typically would write it in, is that the posterior distribution of the test data given the training data is given in the form of a multivariate Gaussian with this mean and this covariance. I think I'm going to pause there before I start talking. I'm going to talk about the covariance function in a moment. So up to so far, I've been assuming sort of your boss gave you this matrix for your training and testing. You know, that's conceivable actually. So I've done some work where I've got a finite number of instances of data, and it's always only ever going to be finite. So you've only got f and f star are a known number, right? So you may be given some number and some other number. That's not full process prediction, that's just working with multivariate Gaussian distributions. And I designed the covariance matrix, but you can envisage that someone gave you those covariance matrices. So any questions though at that point about what prediction with a GP involves? Yeah?
So in your example, we were now only looking at like the correlations of, let's say, adjacent points or also other points, but there's like this additional structure of the wiggling.
Yeah.
Is there a way to capture that?
Yeah, there can be. So that is more on the covariance function, but it's a nice question. So the structure on the wiggling there, what we find is that structure is disappearing if we take many samples. So I said I'm sampling from a zero mean. Look, the mean here, you'll believe me if I say that's zero, right? On average, it's zero. Interestingly, the probability of seeing that flat, that mean function, is zero. You won't ever see that mean function. So even though your mean is zero, and it's the most probable function, you still won't ever see it somehow. But the structure here you're talking about, yeah, it's possible. So we're seeing a little bit of structure. This is, as we'll see in a bit, it's going to come from something called the length scale of the process. How rapidly these correlations fall off, which is actually visualized here on how wide this band is, because we've ordered things in this way. But if you wanted structure here, which might come from periodicity, for example, periodicity is a good example of structure, then you would expect another band in your covariance down there. Visualizing, who here has worked with kernel methods? Anyone else? What sad times. Who here works with deep neural networks? Oh, the same two people. What do the rest of you do? People work with Gaussian processes and I'm thoroughly bored. If you work with kernel methods, these turn out to be kernels, as I have in a future slide. You should always visualize the kernel of your training data, right? Because it's like thing number one that no one seems to do, but you have to do. Because you want to see the structure of it. This is showing you the structure of your training data. We'll come on to that. Probably this is something I should say a bit later. The question is, you need to think of it. And you want to see structure. If you expect there to be structure here, you want to see structure over there. What you don't want is the matrix of your data to be completely flat or completely diagonal, or diagonal plus flat, or something like that. That shows that you're not capturing any structure with the parameter settings of your kernel. But we'll sort of see more about that in a moment. Other questions? So on average, that structure is there, but on average, if we took many samples, that structure wouldn't be there. And that's an interesting question. If you see some sort of data set, are you seeing data structure that is genuinely structure associated with this problem, or is it just coincidence? Okay, so where did this thing come from? Well, we've just started hinting at that. Well, it's actually computed in the case above by looking at the distance between any two of those indices. Now, the indices there were discrete. I equals 1 to 25. But the trick in the process is to say, hey, well, we can make those indices continuous. So what is a function apart from a vector with an infinite continuous index? Okay, if there's any mathematicians in the audience, they're probably dying or something now. But I was trained as an engineer, and from an engineer's perspective, that's what a function is. It's just a vector with an infinite continuous index. So we want to be able to build covariance matrices which are of the same structure. So we're actually obtaining this covariance matrix in the earlier case by looking at the distances between two indices, which would always be 1, 2, 3, 4, 5, 6, 7, squaring it, so this is the L2 norm, dividing it by some length scale, which is giving us that effect of how it's moving, what the scale on the input direction is, and exponentiating it. Now, that looks awfully like a Gaussian density, but that's coincidence. Ignore the fact that it looks like a Gaussian density. It's sometimes called the Gaussian kernel. It's also called the RBF. It's called the squared exponential. I like to call it the exponentiated quadratic to confuse things further. And then it's got another parameter here, alpha, which is giving us the overall scale. So in the previous example, alpha was set to 1 because if the distance between these was very large, e to the minus large number is 0. And e to the small number, e to the 0 is, e to the minus 0 is 1. So the largest you get is alpha. So alpha was set to 1 before. That's giving you the marginal variance at any point. This is a stationary covariance function. It doesn't matter the absolute location of any x. I can mean shift any of these x's and the means get cancelled out. So it makes it stationary. Any covariance matrix that is dependent only on the distance between 2 points is a stationary covariance function. Not all of them are like that, but many of them are. So this object is how I get my covariance matrix. I'm given some training data. So before I was just showing you the y's in effect. They were f's. I call them f's because they had no noise corruption. But where was x coming in? Well, x is coming in constructing that matrix. That matrix is a function of your input locations. So this is a little visualization of what those functions look like that was invented by Philip Hennig again. So Philip, what he's trying to show here is what sort of functions, the nature of these functions. You can see samples, a sense of them in this fluid way. And Philip's idea was to show you like a world tour of a particular set of functions. So the way he's generated these functions is these functions exist in infinite dimensional space. Right? So now instead of taking 25 points here, I'm taking 200. But in theory, I should be able to take infinity. I'm taking 200 and I'm just joining them up to give you the impression of the function. So I can sample an infinite dimensional function, in theory, and it's out there in this infinite dimensional space, like as a vector in this infinite dimensional space. What Philip's idea was then to take an orthogonal direction, and as I pointed out to him, in an infinite dimensional space, all directions are orthogonal, or an orthogonal direction of that function, and look on that orthogonal direction for a function that is of equal probability, okay, to the original function. So this is a little bit like standing on a point on Earth and then looking for an orthogonal point on Earth which is at the same level, the same height, which all points on Earth are at the same point. And then draw a great circle between those and take the tour of that great circle. So take two orthogonal points on Earth and then draw the circle around that defines and go around the circle. And you're visualizing the functions that live along that circle. So I've got a few visualizations like that. Philip has even more. And he's got lectures, if you want to hear him describe that, there's video lectures of him talking about it at the Gaussian process summer school. So that's the nature of these functions. Now, this is one particular type of covariance function, and it may not be appropriate for many, many problems. We'll show you a few more as we go on. So how does that become a matrix? Well, this function is just a machine for generating that matrix. So I'm setting up a little exercise where we've got our famous horrible 3 data points. x1, x2, and x3 are my inputs. I'm not saying what the targets are now, because we're just going to build the covariance matrix, K. We're not building the full Gaussian process, which would involve those inverses I showed you earlier. So all I need to do is compute the elements of that covariance matrix. And since this is my function, I start with the first element in the top corner, x1, and I compare it with x1. And of course, if I put those in the function here, what I find is that the answer to that is 1, because it's e to the minus 0, as I said earlier. Now I compare the distance between x1 and x2, and I place them in here. This is now larger, this distance. So that's a minus minus in there, by the way. So the correlation drops. And it's symmetric, right? So whatever goes in x2, 1 goes in x1, 2. K2, 1 goes in K1, 2. So the diagonal element is always just going to keep dropping out as, because it's a stationary covariance function, just 1. And alpha set to 1. So the length scale here is 2. So similarly, x3 is much closer to x2. So when I compute the distance between this and x1, I still get a low correlation, but I get a high correlation with x2. So now any future observation, so what's this mean in practice? Well, if this was my training data, and this was my test data, when I compute those things before, I'm going to get a strong correlation with whatever this point was. I'm going to get a weighted sum, basically, that says you're very close to this point and not very close to this point. And that's what feeds into my prediction. So similarly, well, this was my training data, so this is something we're doing during the learning stage. We compute this covariance matrix for our training data. But then later we get a test data point, so that's our original covariance. Now for the new test data point, x4, which is at 2, then we need to compute the k star f and the k star star, which is this point down here, in order to make our predictions. So the data feeds in, that's the visualization, to the covariance function in these ways. If we change the parameters of the covariance function, so this is the same example as the first example, but now with a long length scale, a length scale set to be equal to 5. So now we see that we get a very strong correlation between x2 and x3, so strong, and we've also increased the observation of the function, so the overall variance of the function is larger. Now we can use that object in our predictions. So just questions at that moment before I show you the interpolation result of that process of computing the covariance matrix. Anything? So we have software that can do this. I also have Python notebooks online that will do this in a really obvious way, not efficient way, but if you want to sort of learn more. So who's here has used Jupyter notebooks? I said Jupyter. Excellent. Gee, if I'd said that 3 or 4 years ago when I first wrote notebook, maybe I should, at some point, maybe we'll break. We've got an hour of listening. And at the end of the break, I'll show you a couple of little places where you can have a play with this. I don't know how people, some of you I suspect are like, oh God, this is why is he laboring this point? And others of you are like, oh, I didn't get that. So before we break, we'll just take some questions from those of you who didn't get that, or the ones that think, why is he laboring this point? And then we'll go to a quick break. Okay, so questions now. All obvious?
So the simulation that you showed by Philip, is that slice sampling?
No, actually, he did it in a very complicated way, and then I pointed out that it's very easy to do it. I can't remember how the details of his complicated way are, but you can do it just by realizing that the result of what you're doing means you're on a massive circle in an infinite dimensional space, and any circle in an infinite dimensional space will be the weighted sum cosine sine of the two different functions. So actually what you're seeing is a linear mixing of two functions, which took a while for me to persuade Philip if that was the case, but it is the case. It's like, because it's a great circle, as you could call it, tall. So once you've got the 2 points that define the circle, it's just sine and cosine. And actually, once now I've said that, when you look at the animation, you'll be able to see that. And some animations really don't work. I really like the animation. But some animations really don't work because fundamentally underpinning it, that's what it is. That's the problem with these animations yeah. So I look at any one of those functions, and they're actually weighted sums of two different functions. Those things can happen because it's all Gaussian, I suppose. They're quite hypnotic, aren't they?
I'm sorry, I didn't understand the example with the vector and we're going around the Earth to simulate the function.
Yeah, for this, okay, so let me try and, I probably didn't explain it very well, that's probably why I didn't understand it. Philip explains it better. So, in order to get this visualization of the covariance function, I sample one function from the Gaussian process, okay? Now what I want to do, or what Philip wanted to do, was show you a family of functions that are the same probability of that function. So in some sense, that would be, I can use this plot to try and illustrate what he means by that. Any point on this circle is one standard deviation away from the mean, right? So if I sample a function, it could be actually off this, but let's assume we were lucky and it landed one standard deviation. There's a family of circles going around here. So if I have a point here, it's a function with 2 points in it, right? So these functions are really infinite dimensional. And then what Philip does is he then says, okay, I've got that function. Give me an orthogonal direction. So let's say that's the orthogonal direction you choose.
That's also some randomness associated with that, right? In 2 dimensions, no, but in 3 dimensions, yes. And then look along that orthogonal direction for the function, which is the same probability. And then visualize the plot of F1 and F2, but for infinite.
Yeah, so you're visualizing for F1, F2, F3, F4. So the circle is here, the circle's in a plane. The circle we're touring around is in an infinite dimensional space. In theory, of course, in practice, it's on the computer, so it's fine. What was the question behind?
So same question, but could you clarify now how you sample the first 2 points? Like how do you sample the?
Oh, just by sampling, just like I did on this previous slot here. So the first one is just a sample from this full covariance matrix. It's a single sample. So it's actually a weird thing doing this. It's a 25 by 25 dimensional covariance matrix. That's one sample with 25 points. In order to do an infinite sample, I increase 25 to 200.
Okay.
Okay, and I mean, even here, if I were to stitch these things together, you would see it as piecewise linear, right? But at 200, from experience, at 200 you don't see it's piecewise linear. Unless there's really fine-grained scale in the function, which there sometimes is, and we'll see some examples of that later. So, for the purposes of these plots, because humans are very good at seeing the pattern themselves, you don't need to sample that too many to have something that looks infinite. Of course, there's pixels on the screen, so it's fine. Other questions? Okay, so just I don't know if you want to. We'll break for 5 minutes, something just to you can stretch your legs or use the bathroom now. While you're doing that.